Let's now welcome on stage Peter Stoker, Chief Engineer, Connected and Autonomous Vehicles at UTAC. In his presentation, Peter proposes a novel systemic approach and solution for simulation interoperability to integrate various simulation tools efficiently. The advantages and benefits of the presented solution have been demonstrated in a number of use cases and proof of concept projects at UTAC in the last 2 years. Please take the floor, Peter.
Well, thanks very much, and good evening, good afternoon, good morning to all the participants. Great to be back, and a special hello to all our customers. So as well as looking after connecting autonomous vehicles at UTAC, and I'll explain a little more, I have another role as well, and I'm chair of the Euro NCAP Virtual Testing Working Group. So we're looking to how we can integrate simulation into Euro NCAP ratings in the future. The obligatory corporate slides. So about a year ago, UTAC Ceram in France merged with Millbrook in the UK to become UTAC. And typically we work across all the traditional verticals: conventional, future powertrain, safety, comfort, quality, reliability, durability, and connected mobility, which is where my particular focus is, in simulation, in 5G, and in novel test centers. Not one, not two, but 5 proving grounds now fall under the UTAC umbrella. So in France, we have Montlhéry, which is based on a traditional oval racetrack from 1925. We have Millbrook in the UK. In Finland, we have Test World, and a special hello to our tyre customers. Mortefontaine in France, and just opened Udzem in Morocco, which gives us a whole range from cold through temperate through to hot climates. So this is just kicking off right now. At UTAC Millbrook, we decided some time ago that we would not just be one product, one software. We had to be independent and impartial and offer our customers a wide range of choice in all of the software packages and the capabilities that we could put together as an independent test center. So we have a range of dynamic simulation, environment simulations, sensors, traffic, connectivity, which is really interesting, control systems, perceptions, and test and data management. All of this we put together, as Bob has just said, through some hill rigs and simulators, through our propulsion test rigs, and also now, due to our private 5G network, we can actually interact in real time with vehicles on the tracks. We have a series of infrastructure that goes with that: software, hardware, data center, and so on, and it is all linked together by a data-centric middleware. So everything plugs in to this data bus. And essentially, it's all the inputs and outputs are data-centric. We're not exchanging huge, heavy models that utilize a lot of bandwidth. We're exchanging in just very basic inputs and outputs to get this to work as a connected ecosystem. So again, we have the VR-grade compact simulator we've had for a number of years now. Really good. We have a static vehicle-in-the-loop simulator with projection and a whole different suite of software integration. VIL. We facilitate it using our 5G network. So in the vehicle, we have an IMU. That's it. We don't have rigs. We don't have software running. We actually have a real-time connection back to the simulation lab. So actual vehicle setup for VIL is really quite quick to interoperate between vehicles. And this is going to become really important in the future, rather than spending 2 days kitting out a vehicle with a lot of instrumentation. So I'm going to talk about a project that was supported by the UK government, which, bearing in mind this was just a 20-week project, which we ran as a collaboration of different test beds in the UK, different entities. And the whole idea was, can we establish a flexible, integrated framework, demonstrate what's going on in terms of integrated capabilities, so not just discrete simulators, link them all together, start aligning with a test customer, and showcase how we can do this and how bringing it all together can be made interoperable, and how it's much better than one single facility. So the whole idea was to look at customers on one side, whether they be tier ones, universities, small mediums, startups, run through a kind of a UK connected automobility services, a simulation as a service center, and also interlink with each of the test beds that we have in the UK. UK because it's government supported. So, the first question, do we go point to point with all of these software interfaces and spend 6 months writing APIs and test everything out? Or do we put it together on a common data model and try and break this simulation down into a system of systems approach which is going to be much easier to handle and much more expandable in the long term. We could do an ad hoc network just for a concept, but actually, no, we're thinking long term, what is the future going to be? Taking inspiration, actually, from what goes on in defense modeling and simulation, because, again, they're using neutral data buses to exchange differences between their systems and operators. So who was involved? EDADA in the room. Myra in the room. I don't often say EDADA and Myra on one of my slides, but this time they were good cooperators. So for us, we used our driving simulator from VI Grade, integrated that with IPG through concurrent sim workbench. On the tracks, we used real-time data fed into the simulation environment using our 4G, 5G connectivity, and we integrated it through a DDS data bridge. At EDADA, they brought in their V2X hill rig in Cambridge in the UK. So looking at real radio hardware to broadcast V2X messages. And the University of Leeds, which I'll come on to, they have a great pedestrian in the loop simulator, which is called Hiker, which is the world's largest high-resolution CAV-based pedestrian simulator. Ford Motor Company brought the VIL vehicle, and they had on board, that was integrated with IPG CarMaker, so we had an XPAC hill system on side the vehicle, we had access to the ECUs, the camera box, we had access to the Simulink models for each of the control systems within the vehicle as well. Smart Mobility Living Lab in London provided scenario generation, a really interesting methodology to generate scenarios from real CCTV scenes. Myra producing a test oracle to look at the outcome of the simulation, to rate it, study the behavior, suggest further improvements. And WMG in University of Warwick to look at a V&V pipeline. So again, can we look at how we can verify and validate the simulation that we're doing to the real world? We looked at 3 different use cases. So AEB oncoming, latest Euro NCAP 2022 protocols for AEB head-on. Can we break it down to a system of systems rather than just look at it in one big lump? Of course. So you have road, environment, the oncoming vehicle, the sensors, the fusion, the object detection, which forms the system under test. And again, working with algorithms and actuators. We looked at EEBL, Emergency Electronic Brake Light Warning System. So can we produce a real signal from a real vehicle, send it through simulation, and work across a piece of hardware a few tens of kilometers away? So again, looking at forward vehicles, the interfering vehicle as well coming between the subjects, can we energize that? The one just to focus on was an AEB pedestrian, autonomous emergency braking. Again, looking it down into a system of systems. If I take it further, putting it into the operable distributed simulation setup, then we would use the actuator in a hill rig, the vehicle dynamics in the model road, in the environment, a model pedestrian, or maybe even a real pedestrian, we'll come on to that, and the system under test, but all running together in real time using this DDS middleware database. It allows us to do modeling in the loop with exactly the same breakdown and systemic breakdown. So your Simulink models that actually run each of the control systems within the vehicle, running it through with a dynamics model, onto the road, the environment, and the pedestrian. Go a little further and bring the software into the loop system. We can either use a real camera, we can use the C code that actually generates what goes on inside the ECUs, and again, link in with the dynamics. So a lot of this you can swap in and out really quickly. Go forward into hill, so we can bring in the ECUs, we can put a camera in a box. This particular vehicle was camera-only sensor, so we didn't have to go through radar, bearing in mind we only had 20 weeks, and radar's difficult. We can also bring in the driver in the loop, and again, bringing in the driving simulator into the system, running through all of this, again, in real time. And eventually the vehicle in the loop. So put the vehicle on the track, get it linked with a 4G, 5G gateway to report the position back in real time into the simulation, and more importantly, send that position somewhere else. So how do we do it? So I really like the Denisi presentation, and I'll be first there tomorrow to have a discussion about this. So we used AWS and their wavelength network, and we brought together Ford in the UK, UTAC, CAV, which is EDADA in Cambridge, SMLL in London, Myra and Anita in Warwick, and the University of Leeds. And the whole issues that we had to work through was the connectivity side, the data storage, the management, the security. One enemy of low latency is encryption, and it's a complete nightmare. How do we do that in a trusted way? Work out the access level management, and also try and work out what additional processing capacity we're going to need to do this. So this is what we had to do. This is what we integrated together. So you can see the geography on the left, the whole risk list of different things. So some of it bespoke, some of it commercial off the shelf, some of it open source. So simulators, the RF Pro environment, the IPG car maker, Sumo we use for traffic, Aimsong, PTV, vSim, the Hiker Lab in Leeds, the V2X system, vSim, Scoot, which is the real-time traffic light system operating in London. The scenario generator, we'd brought everything in open scenario so we could make it work. A bespoke test oracle, a bespoke V&V loop, and Safety Pool, which is the database for scenarios at Warwick University. So all of this we integrated together. Low latency. It's already been discussed, so I'll skip over this slide. But you know, everybody says, but latency. It's three elements. The individual simulation tools, the network between, as Bob spoke about, and the middleware. And obviously, you've also got refresh rates of projectors, of graphics systems, of renders, and so on. One of the interesting ones that I did find when we talked about this is something that was done in the US recently. If you remember the autonomous IndyCar challenge, where they were racing autonomous vehicles at racing speed, they were looking with the DDS middleware getting down to around about 19 microseconds. So no longer as they talk about milliseconds, we're now talking microseconds, which is really quite interesting if, as you say, we need to stretch the geographies and stretch the links. So for us, it was using a cloud-based architecture, all based around an Amazon backbone. So each particular site had its own IPsec VPN tunnel into their own virtual private cloud. That then linked to the Amazon backbone, and that was sent around the system. So we can connect together Millbrook, London, CAV, the University of Leeds, and run straight through into the customer's cloud as well. More simply, if I just look at it on a simple connection, then this is what we're now putting in place to link to our site in France. So from Millbrook, we'll go down to the Amazon EU West Gateway in London, and they will pick it up in Paris. And we're just about to set that up and see what sort of drop in latency we're going to get between UK and Paris. Next is the Atlantic. So the outcome. This is a great thing by Smart Mobility Lab, which looked at CCTV cameras characterizing all the actors and actually generating in real time a scenario that can be outputted and sent around each of the test beds. Initially, we could do it through Unity and Scala, but it enables us to then convert it into open scenario and run it through the simulation. So this one's particularly picking up an AEB scenario, and later on it does an EEBL. In the University of Leeds, they have the CAV, which is a 9 by 4 meter walking space, glass walls with 4K back projection, and the user wears a very light headset so they can see their own body and interact with the scene as well. And they use motion capture so we can pick up the joints of the pedestrian and produce a model that actually what we were doing is transmitting the position of the model into the simulation at Millbrook, not the whole 3D rendering of the pedestrian. The test environment, we integrated the vehicle with the AEB model, initially in IPG. For more photorealism, we used RF Pro for this particular project. But also there's a great opportunity to integrate more things into open simulation interface so we can actually grow this ecosystem even more. These are the early days. So this is when you don't coordinate your coordinate positions quite well. Instead of walking across, you get a wonderful pedestrian moonwalk. What this is happening, got to show the failures. This is a real person walking around a laboratory in Leeds, 300 kilometers from Millbrook. The position is taken in real time, sent down the Amazon link, and then brought into the simulation. So from Leeds, typically we saw about 3 milliseconds. So when it starts to work, it works the right way around. So if the guy can start, no, back one slide. Start the video. No, back. So actually now the student walked across the Hiker Lab, the vehicle stopped. They stopped, looked at the car, and continued. How did they know there was a vehicle there? Well, we were sending the position of the vehicle on the test track back up to Leeds in those 3 milliseconds time frame. So they were seeing a vehicle model. So this is the view from the pedestrian of the vehicle model approaching and driving past in real time. So the whole thing is to put together an end-to-end tool chain which brings in commercial off-the-shelf simulation software, real-time software and hardware, hill rigs, simulators, real-world data, run through a scenario engine and a simulation manager to give an output. So far, we have integrated the software on the left. We've integrated the rigs that you see in the center and the V&V tool chains on the right. So if you'd like to add to that list, please come and see me afterwards. And just to put it all together, we have the vehicle in the loop rig running, the simulation room, the driving simulator, the vehicle on the track, the real-time capture of AEB and EEBL scenarios from CCTV, the waving pedestrian model, and actually running across the V2X hill rig to pick up the EEBL warning and energize the V2X system. All of it runs through the test oracle to do the analysis, the results, and the recommendations. So that's a very quick run through. That was integrated simulation. I'm Peter Stoker. Thank you for listening.